Hello everyone. In this presentation we'll be covering sine waves, what they are and how they're produced. We will also cover the various quantities involved in a sine wave that you will need for your level 2 qualification. Firstly, what is a sine wave? A sinusoidal waveform, to give it its full name, is produced when a conductor is rotated inside a magnetic field, such as those found inside a generator. This rotation, as we have covered in class, will cause current to flow by producing voltage. The voltage and current will reverse direction every time the conductor rotates 180 degrees inside the magnetic field. This back and forth flow of voltage and current, known as alternating current, or AC, is represented by a sine wave. The two axes, one on the left-hand side and one across the centre, while not looking important, are crucial to completing, drawing and labelling a sine wave correctly, and will give the sine wave meaning in that they represent the voltage scale on the vertical axis and the time scale on the horizontal axis, both of which are necessary to produce an accurate sine wave. As you know, current in an AC circuit will flow back and forth, rather than flow in one direction as it would in a DC circuit. If you picture a fixed point on a circuit, a lamp for instance, the current in an AC circuit will be shuffling backwards and forwards every 0.02 seconds. The resistance of the lamp to this back and forth motion will produce heat and ultimately light as the electrons flow backwards and forwards through the filament. There's another way. If you had a belt sander, the motion of the pad would be in one direction, much like DC, and it will sand the surface but also produce heat as a byproduct. An AC equivalent could be sandpaper, which moves back and forth repeatedly over the same spot, yet, like the belt sander, still sands the surface and also produces heat. So a sine wave shows the reversal of current and voltage. If this was applied to only the vertical axis, it would show the voltage moving up and down as it flowed in each direction. However, this up and down motion takes time, and therefore it is spread along the horizontal axis, creating a wave. Shown on the screen is the current and voltage flowing in one direction as one side of the loop conductor rotates through the magnetic field past the north face of the permanent magnet, and will then flow back the other way as the other side of the conductor passes by the north face of the magnet. So every time one side of the loop conductor passes by the magnetic north, the current will reverse. This is Fleming's right-hand rule in action, as it shows the current flowing in one direction and then the other as the loop conductor rotates through the magnetic field. The first quantity we'll put on our scale is the peak voltage for the first 180 degree rotation. This voltage will build up as the conductor rotates through the magnetic field, reaching peak voltage when the conductor is at 90 degrees through the magnetic field and is at its closest point to the north face. As the conductor continues to rotate and completes 180 degrees, the voltage, and therefore the sine wave, will reduce back down to 0 volts. The other side of the conductor will then rotate through the magnetic field towards the north face, causing the current to flow in the opposite direction, again reaching peak voltage in the opposite direction when the conductor reaches 90 degrees to the permanent magnet's north face. The peak-to-peak voltage shows the full range of the voltage as it flows in one direction, then flows back in the other direction. In an exam, be careful to check whether you are being asked to describe or calculate peak voltage, which would refer to one half cycle, or peak-to-peak voltage, which would involve adding both peak voltages together. For instance, a peak voltage at 90 degrees of 100 volts would also have a peak voltage at 270 degrees of 100 volts. Your first 100 plus your second 100 from each peak would give you a peak-to-peak voltage of 200 volts. One cycle is a complete rotation of the conductor loop inside the magnetic field, and is visualized by the sine wave completing a peak voltage in both directions before returning to the center line. Different rotational speeds will give a different frequency, but in the UK the conductor will fully rotate every 0.02 seconds, giving us a frequency of 50 Hz, which we'll explain on the next slide. Frequency is determined by the amount of time the conductor takes to complete a full 360 degree rotation inside the magnetic field. To calculate this, you divide 1 second by the time taken for that complete rotation. As you saw previously, that time is 0.02 seconds, so your calculation would be 1 divided by 0.02. This would give you a frequency of 50 Hz, which is the standard frequency in the UK. Alternatively, if you know the frequency but not the time taken for a rotation, you can calculate this by dividing 1 by the frequency. For this example again, it will be 1 divided by 50 Hz, and this will give you an answer of 0.02 seconds. Pay attention to any exam questions with these calculations, as they may not be asking for 50 Hz or 0.02 seconds. You could be asked to calculate the time period for a different frequency, such as 80 Hz, in which case the working out is still the same, but you'd use 1 over 80 rather than 1 over 50 to get the time period. Back to sine waves now, to something you're almost guaranteed to be asked in an exam. We've covered peak and peak-to-peak voltage previously, and we're now going to look at average values and RMS values. Average value is determined by dividing the first half cycle into a set number of evenly spaced vertical sections and measuring the voltage at each point as it goes up from 0 volts up and over the crest and back down to 0 volts again. You then add up the voltages from each point and divide your total voltage by the amount of sections, giving you your average voltage. This will always be your lowest figure compared to the peak and RMS values. The RMS voltage, which stands for root mean square, is the equivalent voltage it would take a DC circuit over the same time period to produce the same amount of power. You can see that AC has to produce a higher peak to account for the rise and fall in voltage across the half cycle. To calculate, you again divide the half cycle into even sections and take the voltage at each point as it increases and then decreases. You then square the voltage from every point and divide the total by the number of points taken. Finally, you need to find the square root of that sum. It's worth noting that the RMS voltage is what we use to describe the level of voltage in the UK in an AC circuit, meaning that the 230 volts we use in this country is not peak voltage, and with a quick bit of maths you can see that the peak voltage will actually be 325 volts. Here are the calculations to get your average or RMS voltage from your peak, or to get your peak from your average or RMS values. If you're unsure which way around they go, then remember that your peak voltage will always be your highest figure, your average will always be your lowest, and the RMS will sit in the middle. If you're not sure whether to multiply or divide by 0.707, and when you calculate them to find you've got these in a different order, then just recalculate so they're the correct way around. In an exam, you may be given an average figure and asked to find the RMS. It can be difficult to get one into the other, so in this instance you would take your average and find your peak from that, and then once you've got your peak you can then find your RMS voltage. This is the easiest way to work around the question rather than trying to get from 0.636 to 0.707. This will also have the advantage of giving you an average, an RMS and a peak voltage, in which case you can check your answer to make sure all three are the correct way around.